All right. Hello, everyone. Thank you so much for coming out here, and welcome to this third lecture on Bitcoin. Today, we'll be going over Bitcoin mechanics and optimizations. I hope you all can see my screen. If not, just type it in the chat or wherever. And if you can't hear my audio or if there's any technical issues going on, just feel free to let us know. We'll help you all out. So my name is Sashir. Oh, just a little bit about, okay, real quick. Okay, so today we'll be going over Bitcoin mechanics and optimization. So far, I think we've talked a little bit about Bitcoin, just some higher level overview of what it is. But today we'll be going a little bit more in depth about its functionalities and what truly it is at its very ground level. So really excited to get started with this. So today we'll be going over cryptographic hash functions first, and then tamper-evident database, and then 6 ECDSA and addresses, and then ultimately finishing up with Bitcoin script. These all kind of maybe sound very heavy, but trust me, it's at its fundamental level. If we break it down, it's just some basic things that Bitcoin has just accumulated and put it into one great piece of technology. So just introduction, I am Sashir Giri. I am a consultant. I'm a consulting developer here at Blockchain at Berkeley. I've been in Blockchain at Berkeley for 2 semesters now. Well, wait, I joined last semester, so you can count this semester as like my 2nd semester. And I'm currently working on external projects. So that is something to look forward to. And I just recently merged my Bitcoin PR and made some contributions to the Bitcoin core. Obviously, that's a little bit of a flex, I would say, but you know, it's healthy. So, and Hannah.
Yeah. Hi, everyone. I'm Hannah. I'm a 3rd-year student at UC Berkeley. I'm part of the education department here at Blockchain at Berkeley. This is my 3rd semester in the organization. So currently what I'm doing right now is leading an internal project within the education department. I've also run the student facilitated course version of this webinar through UC Berkeley last semester. So, and yeah, I'm excited.
Okay, now let's get started. So before starting this, I just want to let you all know that please, we love questions. Even if we can't answer them, we will try our best to do some research and then get back to you via email or any way to answer your questions. Any questions that you have, there is no right or wrong questions. Anything that you have, please feel free to talk to us and let us know in the chat or Q&A, and we will do our best to answer your question to the best of our ability. So without further ado, we'll get started. The first thing we'll talk about is cryptographic hash functions. And the cryptographic hash functions are basically a simple kind of functions where you pass in something and then you get an output. Now, there are several properties that you can classify these output as, and one of the best thing about cryptographic hash functions, that what it's popular about is whenever you pass in any amount of output, whether that's a very small output just containing a digit or a massive output containing millions of data, it's just gonna give you a very limited size data. And that is as random as it could possibly be. It's just like flipping a coin in every single bit. So every single letter that it produces, it is completely random. So that is one of the major functionalities and why cryptographic hash functions are extremely known for. Now, why is this important? It is very important because we always have this question in the back of our head, even the people who develop Bitcoin and wrote the white papers, everyone who's concerned about security and technology definitely has this question in mind at some point in their life, that how do we ensure some amount of trust in a communication in a trustless environment? Bitcoin is obviously decentralized, where the idea of trust, there is no idea of trust. We trust the network, we trust the proof of work mechanisms. So how do we establish some kind of trust in that certain system? So with cryptographic hash functions, we actually can figure that out. There is a mechanism we can use with cryptographic hash functions, and we can maintain some kind of trust between different individuals. And one thing that I would like to mention, which we'll talk about in detail later on in the slides, is it is extremely, very, very extremely highly used in digital signatures. And what digital signatures high level basically are, it's just producing different kind of cryptography keys. Like for your accounts, for whatever it is that you need, it is extremely used in digital signatures. In fact, cryptographic hash functions was originally proposed to find a solution for digital signatures to begin with. So that is extremely, extremely popular, digital signatures. So as I mentioned, before talking about cryptographic hash functions, I would just like to say what a function is. A function is simply, there is an input, and a function is just some kind of procedures that takes place with this input and outputs something. So in this slide, you see X is one of our input. We go through this thing, this middle block, and then we produce f of X. That is our output. That is generally what function is. Now, a cryptographic hash function is pretty much the same thing, but few terminologies that's kind of different. Now, instead of X, we have some kind of message that we're sending. And then in the middle part where there are procedures and properties of the function, those are called the hash functions that we are going to do. And then the output that we see, the f of X, is actually called a digest. And some other languages are not net languages, but like some people like to call it hash, some people call it tag, some people just call it output. So just to give you guys some terms to introduce with. And as I mentioned earlier, one of the key properties is regardless of how big the size is for your data, when you run it through a hash functions, it usually gives out a very limited amount of bits. So the recent example that I can give you is something called SHA-256, which is widely used in Bitcoin. Regardless of how big your size is, regardless of how big the transaction data is, whenever you hash that, you're always going to get like 256 bits of your data. So that is one of the core functionalities. Now, I kind of highlighted on some of the properties of cryptographic hash functions. Now we'll go more in depth about specific properties. The first one is it is computationally efficient. Second one's collision resistance. And third one's it hides information very, very well. And you can see this image out here. And let's say these are just our messages. They go through some kind of hash functions, and these are the output that you see. And what this picture is generally trying to show you is even if we just change one letter in our sentence, the entire hash is different. So these are generally the same sentence, like I am Satoshi Nakamoto, and then we've just changed the numbers at the end. But if you see the hashes, it's significantly different. It's completely different from what it was before. So that is one of the core features as well. So we'll dive deep into these three functionalities, these three properties, I'm sorry, and we'll look more into them. So the first thing is it's computationally efficient, which generally means that whenever you're trying to create some kind of hash, it doesn't have to take seconds or minutes that you'd have to wait in front of a computer to generate a hash. It has to be pretty efficient to a level where you can generate it instantly. That's generally the idea, but you also can't make it so fast that if you're trying to decrypt it, if like hackers are trying to figure out the alternative and get to your original message, it shouldn't be that fast that they can just do it instantly. So you have to find some kind of threshold, some kind of middle point where your hash function is fast enough for users to just generate it, but slow enough for the hackers that would take exponentially, pretty long period of time to generate the original message. So that is one of the key properties of using these cryptographic hash functions. The second property that we use is called collision resistance, which the term's kind of fancy, but it generally means that whenever you go through a hash function, it's one of the biggest security issue that we might face is what if two outputs have the same value, right? What if two inputs, have the same output? So that is a very, very critical issue in any kind of hash function that you see. Obviously, no hash functions are, are very immune to these, regardless of how well it's made. There is nothing called absolute, like absolute resistance, absolute collision resistance, but it is exponentially difficult. It is astronomically difficult to generate two hashes, two outputs from the same input. And if you just take the perspective, like an analogy, I can give you a little example. Like, let's imagine if every single computer ever made by humanity was computing since the beginning of the entire universe all the way up till now, the odds that they would have found a collision, meaning two hashes being the same, is so small. It is exponentially, it is astronomically small. So if all the computers in the beginning of the universe was computing, it is extremely small. The chances are very small. So you can guess how difficult it is and how challenging it is. So the third thing is hiding information. What it generally means that whenever there's an output, like we saw in this slide out here, that even if we change one thing, everything is different. And what it generally means that the output should look extremely random than what the input was or what the previous output was, that two outputs can't look alike. Even if it's just slight change in the variable, like instead of odd numbers, you put an even number. That should just change the entire hash. And that is one of the key features. So just to recap real quick, the three key properties of cryptographic functions are computation efficient, meaning the algorithm has to be efficient enough to get the hash immediately. Collision resistance, meaning two outputs can't be the same, not necessarily can't be the same, nothing's immune, but it has to take a hacker or a person astronomical amount of time or a significant amount of time just to generate two same output. And hide information, meaning the output should look pretty random to the rest of the output that's been generated. And this ties along the same idea. So the terminology for hiding the information or making sure the output looks random is called avalanche effect, where basically the output is pretty different. And this is the same picture as we've put before. So real quick, this is in scope of Bitcoin. Bitcoin uses SHA-256. It uses it twice, so it squares the hash so that it's more secure. And this is SHA-256 is one of the most popular hashing algorithm out there, cryptographic hash functions out there. Back in the days, it used to be MD5, which Google and Yahoo and everyone else used to use. But as computers got advanced, they started finding two outputs of the same input. So MD5, MD1, MD2, like those hashes are pretty obsolete as of now. And SHA-256 is the latest one that is very popular. Are there any questions? Okay, feel free. There's no right or wrong. And okay. And if you don't want to talk as well, just shoot us a chat. It's like, just send us a message on the chat or the Q&A, and we'll be more than happy to help you all out. So since you don't have any questions, we'll move on to our next section, which is tamper evident database. The name kind of sounds strong, but trust me, if we just go deep into the process, it's very fundamentally basic ideas. So this figure, this image that you see out here is what a Bitcoin block looks like. So we've talked about blocks, connecting blocks, blockchain is basically blocks being chained together. But what is all of that? We're going to go deep into what actually what people mean by the idea of blockchain itself. And we're going to see that in terms of Bitcoin. So these are some of the key properties, key components that a block has in Bitcoin. There's the idea of block header, the previous block hash, nonce, and then Merkle root. And then first thing real quick, a block header is the hash, is the cryptographic hash of all these three components. Like there's the previous block hash, and then we hash that with Merkle root, and then we hash that with the nonce, and that way we get the block header. in terms of mining, which we'll go over down later in the slides, the miners actually have to guess the nonce to generate a block header and then ultimately validate those as well. So real quick, we'll go over Merkle root and what it is. And then we'll go over the previous block hash and the nonce. So a Merkle root is simply, so a Bitcoin block can consist of lots of transactions. It doesn't have to be one transactions. They can consist of, I think right now it's around like, it's quite a hefty amount, like ultimately 1,000 maybe. I'm not sure about the data, but it can consist of a lot of transactions. But the idea is we have to create this blockchain in a certain way that if we tamper, if we try to edit the previous block, the block following has to be affected, okay? And then for that to happen, we have to construct our transactions in a certain way that if we just try to modify one thing in our entire transactions, the rest of them is false. For example, I'll show you. So these are the 4 transactions that's happening in a block. Let's say for an example. So what we ultimately do with these is we try to hash these transactions that's in the first level, that's in the second level from the bottom that you see. So that's, we put some cryptographic hash in them, and then we hash those transactions. Then we hash A and B to get E, and then we hash C and D to get F. And then ultimately we hash those 2 as well to get the final hash. So what happens in these kind of system is, let's say you wanna go back at the beginning of Bitcoin, let's say, in like 2008, 2009, you just want to modify some block. You want to modify this transactions, and then instead of putting 2 Bitcoin out there, you want to put 200 Bitcoin to get rich. So when you try to do that, what happens is the hash of this transaction changes. And that basically means that the hash of this changes, the C and D, because it was made from the C block. Ultimately, that changes the top level Merkle root as well, because everything is being hashed and it's just being brought down to the Merkle root at the very top. So when that happens, obviously that's not the correct block. So you won't be able to do anything with it besides get false information, or not necessarily anything whatsoever. And that is the power of blockchain, that whenever you start tampering with the previous blocks, the blocks that's ahead will get affected as well. If you tamper it effectively, you'll get affected, but the idea is you just necessarily can't do that, because the blocks ahead are honest blocks, and those are made from these existing blocks. So this is the idea of Merkle root. And also one of the benefit that it serves is that, let's say, like to run a Bitcoin node, like you don't necessarily have to be a miner, or to validate some kind of transactions, you don't necessarily have to be a miner. You can honestly run some kind of Bitcoin SPV nodes, which is like payment processing node, on your phone as well. And to do that, you can actually, and let's say you just want to verify whether this Merkle root is correct or not. And this is a little bit mathematical, but if you don't follow up, that's completely fine. This is a little technical. So let's say you want to verify this Merkle root. So you don't necessarily have to go to all the transactions and verify those. You can only go to E, which consists of A and B. Then you can go to C, and then you can go to D, and then you can go to E and F. And that usually takes less amount of time to traverse through the Merkle root and verify that it's correct. So that is just a little mathematical idea, but that is one of the co-features of Merkle root as well, besides the security aspect of it. And one quick question you might have is, what happens if there is an odd number of transactions? Let's say this is an even number, and we're like pairing it up together to get the top level Merkle root. So whenever there's an odd number of transactions, the odd number basically replicates itself and then makes it even. So that is Merkle root. Do you have any questions? Okay, and feel free to type it in Q&A or chat or wherever you can, and we'll be more than happy to answer you. Okay, seeing none, I will move on. So we just talked about Merkle root. So just imagine that this is the top level Merkle root that we saw out here. So the top level Merkle root is generally this one. And it's nothing fancy, it's just a hash, a 256-bit long hash that we talked about in the cryptographic hash function section. So we have the hash of the Merkle root. Now we start talking about the previous block hash. And this is where the chain comes in blockchain. This is the block, previous block hash is like the chain. So if you see this diagram, this is essentially what the idea of blockchain in picture looks like, that the previous block hash works as a chain. So as you can see here, the block header in this becomes the previous block hash, and then the block header in the middle one becomes the previous block hash of the far right one. And what block header, as we talked about, is generally the hash of Merkle root, previous block, and nodes. So if anything in Merkle root gets tampered, then the block header obviously changes because it's the hash of all these three. And then when block header changes, the previous block hash changes so that this far right block would not be a valid block. That is the idea. So as I talked about here, so let's say if the middle one gets tampered, I mean, the previous block hash changes, which basically means that that block is a dishonest block. And the idea is that the miners always want to mine in the honest block. So the idea of good and bad, which node is good, which node is bad, no one knows that, not even the miners. So what they generally do is they generally try to mine and then push it to the longest chain out there. So you can actually make forks of this, which we'll talk more about in detail. So there's an ideal blockchain that's going through one lane, and you can make another lane going through it. And let's say that lane has more blocks and people trust that block more, then that's what's going to get pushed at more, and then that would be your longest chain. So this might sound a bit, a bit confusing at first, but we will go through these systems like in the forking lessons, and then hopefully you'll be able to understand, but that's generally the idea. So is there any questions in previous block hash? Okay. Oh, wait. Okay, the question was, can I go over the Merkle root real quick? Okay, I can do that. So Merkle root is, once again, it's just, so Bitcoin block has lots of transactions. In this instance, we are just taking an example that there are 4 transactions, okay? These 4 are the transactions that's inside a block. And what our purpose, what our ultimate goal is to merge these transactions in a certain way that we just get one hash at the very top. And that would be our Merkle root hash. So let's say we have 4 transactions out here, and we want to get one final hash that conquers, that like takes care of all the rest of the transactions. So we hash these transactions first. So there's a systematic process of doing this. So we hash A first, we hash B, we hash C, and then we hash D. And then we go up to hash A and B to get the hash of A and B, and then we go up to get hash of C and D, and ultimately we hash E and F. So you can see we have A, B, C, D as our original transactions, and then E is like the hash of A and B, and then F is like the hash of C and D. And then ultimately, we don't care about these anymore because we have their hashes. We don't care about A, B, C, D anymore because we have the hashes of E and F. And if we hash E and F, we can get the hash of A, B, C, D. And what hash of E and F up here basically means, like right here basically means that E consists of A and B, and then F consists of C and D. So ultimately, we're just hashing everything and creating like a tree. Does that kind of make sense? Yeah, I can't really open up questions, so I'm not very sure about what questions you're asking. Let's try this. Yeah, I can't really open up Q&A, but Okay, there's a question. Wouldn't the verification honesty need to be done before the block joins the chain? Otherwise, the whole chain becomes dishonest. Well, the idea is whenever you're pushing a chain, you just have to guess the nonce value. And then ultimately you can do other stuff with the chain, like have a dishonest chain. But yes, ultimately it would just come down to the verification process, and everyone just follows what the longest chain is. The idea is to follow the longest chain. Okay. So yeah, I can't really open up Q&A. So guys, I'm so sorry. I can't see the questions, but hopefully you can just put them in the chat and I'll do my best to answer them. Yeah, I can't, whenever I click the Q&A, it just doesn't load or doesn't show up at all. Okay, yeah, we'll move on. Okay, so last thing is we're just trying to get the idea of nonce. We know what previous block hash is. This is generally the block header of the previous block. And there's the Merkle root that is built up by the transactions. And now we're going to talk about nonce. So before talking about nonce, we should definitely go over a little bit about proof of work. And proof of work is what actually made Bitcoin so essential, because digital currency existed before Bitcoin. There was obviously lots of other coins that existed, but what made Bitcoin special was they were able to do it in a decentralized fashion. There was no um, middleman trying to verify transactions or whatever. So proof of work is generally a vehicle in which someone can show that they have engaged in a significant amount of computational effort. That sounds kind of technical, but it just generally means that it's a verification process which shows that you have engaged with a significant amount of energy and processing. That is generally what proof of work is. And it'll make more sense when I give you an example of how it was actually invented. So proof of work was basically at the very beginning created to prevent spam emails. So in regular emails, regular mails, like post mails that you see, we have stamps at the very top right mostly. So you just stamp it and send it to whoever you want to send it to. So they were trying to mimic the same, like similar functionality digitally, but instead of the post stamps, they were trying to do that with computational, like energy, how much computational effort does it take to actually send those. So whenever you're sending an email or two, that doesn't require a lot of computational effort. But whenever a spammer is trying to spend 100 or 1,000 emails, then that requires a pretty high computing power. So you can kind of predict that that would be a spam email. So that was the idea of how proof of work kind of got started, and it was highly popularized by Bitcoin, obviously. So in proof of work, there are three major components. The first is computationally. It has to be computationally difficult to generate or to solve something in proof of work. It has to be extremely adjustable, and it has to be verifiable, easily verified. And we can see how Bitcoin does that in coming slides. So the idea of nonce now is whenever, so this is where the idea of mining comes in. So whenever you're hashing these three values, so I talked about hashing these three values to get the block header. So whenever you hash these, obviously you can find the Merkle root. You are also given the previous block hash. What miners need to find is this nonce value. And nonce value is just a random value that is determined by the difficulty level of the network. And whenever you hash those three together, there is a target value that's already being set. And whenever you hash these three values, like previous block hash, Merkle root, and nonce, then you will get a certain hash, and that has to be less than the target value or pretty equivalent to the target value. Then that verifies that your block header is correct. Now, this might sound a bit confusing, but we're actually going to see examples, and it'll make more sense. Hopefully, it'll make more sense. So this is what the target value looks like. Don't care about anything that's after F. We only care about the zeros, that's before F, and those zeros are the ones that direct how difficult it is. So we have 4 zeros right now, so that means the nonce value is going to be 4-digit long as well. So whenever someone predicts some kind of nonce value, then they will get something like this kind of output, and that generally means that they have that the output is correct, that the nonce value they predicted is correct, and then they can push it to the chain now. So we're just trying to be a miner and trying to guess the value right now. So we guessed hello world, and then we guessed 0, and then we got this as our hash value, which is in red, which obviously is not less than or even equivalent to what the target value is. So we keep guessing, we guess 1, that's obviously incorrect. Now we guess 4250, which is 4-digit long. So, oh, sorry, which is the same thing as the target zeros. So that is where the idea of guessing the nonce is. And you can have strategies to guess the nonce, but ultimately it just comes down with, you know, randomly guessing these values and then hashing them. So you're guessing, hashing, checking, guessing, hashing, checking. You just do that millions of times right now. And I'll actually show you towards the end how difficult it is, or the difficulty number in the current Bitcoin chain. Okay. And so the idea of, so that was the idea of basically, it's a simple idea of mining. And I said mining is an extremely difficult process. It's ultimately like throwing darts at a board blindfolded. You ultimately have to guess those numbers. Obviously, the thing is people who have more computational power has more advantage over the people who doesn't have that much computational power. And that's just because they can guess values faster. And then real quick, the way Bitcoin difficulty is being decided is, I think it changes or adjusts over every 2 weeks, which is around every 2016 blocks. So whenever 2016 blocks has been mined, then the difficulty changes, and it changes based on the hash rate, or basically meaning how fast or how slow the block has been created. And there is a time frame. There's a constant time frame of a block has to be created every 10 minutes as well. So based on that time frame, the difficulty is adjusted in the Bitcoin chain. And there's no person changing these. It's just the algorithm and the consensus, the proof of work consensus that's been written. That is actually what decides these. And obviously, as I said previously, the zeros are the ones that determines the difficulty of actually mining a Bitcoin. So if there are more zeros, then it is significantly difficult to mine it in compared to less zeros, because then you're guessing, like if there's 1,000, then you're just guessing 1,000 numbers. If we add one more zero, then it becomes 10,000. So you can see the more zeros you add, the more difficult it becomes in the target value. So this is what the code looks like for nonce, just general code of how to guess nonce, and the mining procedures look like. And real quick, I just want to show you guys what an actual Bitcoin block looks like. And we're going to see nonce values. We're going to see previous block hash and everything. So I hope you all can see my screen. So this is actually the page. Since Bitcoin is pretty open, everything is online, all the transaction details, so we can actually see what's happening in the network. So if we see the latest block right here, this was mined 17 minutes ago by unknown miner. So this is the ultimate hash, which is basically the block header we talked about. And you can see all these zeros out here. So these are what determines how difficult, the difficulty level of this transactions, or of this block. So if you count, these are around 19 zeros. So you can see how long it actually took to mine that. And if we scroll down, we'll see the difficulty number. This is basically the nonce. Well, no, this is the nonce that they calculated. And then it ultimately ties down to the zeros when they hash that to the Merkle root that we see, right, that we went over right here. And then they should have the hash of the previous block somewhere. But whenever you mine these three stuff, no, you don't mine. Whenever you hash these three stuff, you ultimately get this hash, and that verifies that it is a legit block. And you can see the transactions as well. Ultimately, and the block reward and fee and everything else as well. So it's pretty much most about the Bitcoin block and what's within it. Are there any questions? The slower the computations, the more difficult, and the shorter the chain. Well, the slower the computations, the easier it is. So if less people are actually, well, if the hash rate is very small, basically means not a lot of people are mining it, then the difficulty comes down to very slow, because we're incentivizing miners to mine it and then put it in the chain. That is what the idea of decentralization ultimately is. So whenever there is slow processing and people aren't mining it as much, then the nonce decreases, ultimately meaning that the blocks, it is pretty easy to guess the nonce. So can you imagine and walk us through a scenario whereby our transactions represents the movements of the drug compound through a distributed system? Would this allow tracing a lot of easily? Well, yeah, the idea is, as I showed you in something like this, you can actually see what's being mined. So this was the previous block that was mined. And then this is the current block that was mined, all right? That was, oh, it changed now because it's 1 minute ago. You can actually trace down. And what's great about this, as you talked about finding the supply chain and then going up to the ultimate thing, is you can see the transaction hashes as well. So you can actually go back and then that is a great question when you talk about like the Bitcoin transaction system. So the transaction system is so efficient in Bitcoin is you can actually trace it down to the first transactions that was ever made. So you can click on this, you can see the hash, and you can actually see where this came from. And then you can see what the previous one came from, and you can just keep on going back, and then you ultimately find out who made the first transactions, and ultimately that would eventually start. But in case of something like as you talked about drug compounds and all, you can actually figure that out because it's mostly being transactions, and you can just go back into the chain and then figure that out. Okay, are there any other questions? Okay, I hope that I answered that pretty well. If not, I would just type the message in the chat and hopefully I'll be able to answer it better. Seeing none, there's a little bit of break now. And then our next lecturer will be Hannah. We'll be going over the rest of the presentation. Thank you so much, guys.
Right. Would everyone like a 5-minute break? I think we have enough time to have at least like one 5-minute break, and it might be good to have one because with my section, we shift gears a little bit. Or would everyone like a break? Right. Then I think a break would be good. So, or like are the moderators like okay with that? The other panelists? Okay. All right, then we'll continue the lecture at 6:50. And then from then we'll start discussing signatures and addresses. All right. Can everyone see my screen? Okay. Can I ask if everyone is back at this point, and are y'all ready to begin the next section? Okay. So, all right. So next section. So this section, we're going to shift gears a bit. So in the previous sections, we've taken a look at how like the overall data structure is secured through it being tamper evident. But now we're going to shift gears a bit and examine how individual transactions between users are secured. So we'll be discussing generation of private keys, public keys, signatures, addresses, and more. Okay. Oh, okay, there you go. Okay. All right, so when it comes to securing transactions, we seem to have this dilemma. Like we want to be, okay, so we want to be able to achieve two things. We want to first be able to tie a specific identity to a transaction to confirm that a certain user sent it. So that, but like at the same time, like when we make a transaction, we don't want anyone just looking at the transaction to be able to recover like sensitive information about yourself. Because like if they are able to recover this like sensitive identifiable information, then other people can possibly break into the UTXOs that you own and then like spend your Bitcoin and steal it from you. So, but these two properties seem to be pretty contradictory. Like, how can we make it so that we can achieve both at once? All right, and Bitcoin goes about doing this by implementing public key cryptography. And general definition of public key cryptography is that it's a cryptographic system that allows for the secure dissemination of identity and the authentication of valid messages. So there are two pieces of information that really form like the cornerstone of public key cryptography, and that is the private key and the public key. So first information that I have on the slide here is the public key, but I'll be discussing the private key first. I think it'll be more logical that way. So a private key is essentially the sensitive information about a user that you don't want anyone else to know about. Like this private key should only be known by the original user themselves. And because oftentimes the private key is used to or at least in the context of Bitcoin, the private key is used to actually access your funds. So you need your private key in order to be able to send funds to other people. On the other hand, you also have your public key, which is generated from your private key. And your public key, this is information about yourself that you can distribute widely. And this public keys are generally used to be able to receive transactions from other people. All right, and well, so the particular algorithm that Bitcoin uses to generate public keys and verify transactions as belonging to certain users is called elliptic curve digital signature algorithm, or as we will call it from like this slide onwards, ECDSA, because the actual name is really long. And ECDSA is a variant of the standard digital signature algorithm, or DSA, but it includes an additional layer of calculations using elliptic curves. All right, so now we're going to get into just a general high-level like walkthrough of how signature generation and verification works in Bitcoin. A couple things, disclaimer. So this isn't the complete story of what happens when you are making a transaction or sending a transaction through the Bitcoin network. This is more of a general representation or an analogy of a transaction verification using ECDSA. So this doesn't include all of the granular details. But let's get into the example. So say that we have two people on the Bitcoin network named Alice and Bob. And Alice wants to send some Bitcoins to Bob. Good for Bob. I wish somebody would do that for me. It's okay. I don't really need it. But before like everything else, Alice needs to generate a private key, and Alice will do so by using a cryptographically secure random number generator. And we'll go into more detail why, like you have to use a very specific type of random number generators later. But yep, first things first, Alice needs a private key. So Alice makes a private key. Yay. The next step is to generate a public key that corresponds with your private key by using ECDSA. All right, so Alice's public key, since her public key is considered public knowledge, I say public in quotes, it really means that this is information that it can be safely distributed to anyone else in the network. So because Alice's public key is meant to be shared, she will send her public key to Bob, and Bob will have this information readily on hand. All right, so now Alice has some transaction that she wants to send to Bob. So she creates a transaction, but before she sends the transaction to Bob, she also wants to create a signature that will allow her to verify that yes, she is the person that created this transaction. And so in order to create that transaction, Alice needs to first hash her transaction. So she produces a transaction hash. And then using her private key and the transaction hash, she'll produce a signature. And she'll also use the elliptic curve while I'm trying to calculate the signature. All right, so now Alice has everything that she wants to send to Bob. So she'll send her original transaction and her signature to Bob. Yep. And now Bob has three pieces of information on hand. He has Alice's public key, her transaction, and her signature. But now Bob needs to be able to actually make sure, oh, like Alice actually sent this transaction. So with the power of math, Bob will be able to verify if Alice created the signature by using her public key, the transaction hash, and Alice's signature. Because if Alice is the one who created the signature, then the math will work out in such a way that Bob will be able to verify, oh yeah, things line up. Alice indeed made that signature. And additionally, Bob will be able to recreate the transaction hash that Alice made to create the signature, because the cryptographic hash function used to create that hash is also public knowledge. So Bob will be as long as Bob has the original transaction, he will be able to recreate the transaction hash. However, even though Bob may be able to verify if the signature indeed was created by Alice, Alice still won't be able to easily recover her private key. And this is because it is very difficult to reverse engineer the private key from a public key. And we'll go into more detail why in a little bit. So now we've achieved our two goals. So Alice was able to confirm that, yes, like I made this transaction, this is mine, but without ever having to show Bob her private key at all. And so Bob won't be able to like access her other UTXOs and like take her Bitcoin. Okay, so now let's say that we have a malicious third party named Eve, and Eve wants to tamper with Alice's transaction for whatever reason. So Eve also has her own private public key pair, And her private key will denote by the green key up on the slide, and her public key is denoted by the cyan key. Okay, so let's say that somehow Eve was able to get her hands on the original transaction that Alice made, but Bob hasn't gotten it yet. So Eve is like, okay, well, I want to be able to pass off this transaction as my own. Like, I made this, not Alice. So even if like Eve tried to pass off the transaction as her own, Bob will be able to verify that Eve didn't make the original transaction. Okay. Oh, when I got a little ahead of myself there, but okay. So Eve has the original transaction. She creates a signature. She creates her own signature by signing the message with her private key, not Alice's. All right. And then after creating her own signature, Eve sends the original transaction and her signature to Bob. But by running through the signature verification algorithm with Alice's public key, but with Eve's signature, Bob will still be able to tell that no, Alice didn't create the signature, because even though the original transaction and the transaction hash still remains the same, the signature is fundamentally different because it was produced using Eve's private key. So thus users can't pass off a transaction as their own if they weren't the original intended sender of the transaction. Okay, so this signature generation and verification algorithm allows recipients to verify these three properties with their transaction and signature pair. So they'll be able to verify that, yes, the original sender of the transaction had actually authorized the transaction. Additionally, it is also so that the original sender of that transaction, or AKA the owner of the private key, cannot backtrack, as in, like, after they send the transaction, they can't at any point after that, like, be like, oh, I never made that transaction. What are you talking about? Like, you're just imagining things. They can't do that because Bob will still be able to verify that the signature as belonging to Alice. Additionally, the signature proves that the transaction, because the signature also proves that the transaction can't be modified by anyone after it has been signed. Because if the transaction becomes tampered with somehow, like after the signature has been created, Bob will be able to figure out that the message has been tampered with because he can just simply run the tampered message through a cryptographic hash function and be like, oh wait, like that's not the same hash, because cryptographic hash functions are deterministic. So if he hashed the original message at any point, then he'll be able to easily tell, okay, no, the message got tampered with. All right, any questions? I hope I was able to walk through that clearly. Look at the... Right. Okay, I'm not seeing anything in the chat. So if you do have any questions about the signature verification and generation algorithms, later at any point during this lecture, feel free to send it into the Q&A. Okay. Need to bring up our notes again. Okay. Okay. So, all right. So now we're gonna discuss actually how we're going to go into a little bit more detail as to how private keys, public keys are generated, but also beyond that, how public key hashes and Bitcoin addresses are generated. Because the previous example wasn't really it wasn't an exact representation of what actually goes on when sending Bitcoin to other users, because you do not send Bitcoin to public keys. You send Bitcoins to Bitcoin addresses. And we'll see like how that is generated through these slides. Okay, so yeah, here, so here in the slide, we have a flow chart that represents like the process the protocol goes through to go from your private key to generate a unique Bitcoin address from that private key. So we'll step through this flow chart just one step at a time. And then, okay, so before anything else, we need to generate a private key. Okay, so in Bitcoin, private keys are basically just 256-bit unsigned integers. So, okay, they can be represented, they're often represented in different bases or formats, but at the end of the day, they're all 256-bit unsigned integers. So we'll also find that private keys on Bitcoin are cannot be generated using regular random number generators, because traditional random number generators are not actually truly random. They're often deterministic to some degree. And unfortunately, because they are deterministic to some degree, they're not the most cryptographically secure numbers. So instead, we don't want to use those random number generators for generating private keys. And there are many different methods and ways to go about generating like secure private keys for Bitcoin, but some methods are more secure or convenient than others. And we'll often find that in real life, private key generation is often like handled for you in wallet softwares. But at the end of the day, like they're all using like some random number generator to create the private key. Okay, so because the private keys are randomly generated, there's a little bit of that like underlying fear that, okay, well, like what if two different individuals accidentally end up generating the same private key? So this means there is another person out there on the network that can access my UTXOs. And this event is called collision. And you'll definitely remember this from Shashir's portion of the lecture. But the chances of two different individuals generating the same private key is extremely low. And this is because there is approximately 2 to the 256 power unique distinct private keys. I say approximately because the actual number is a little bit less than that, because not all of those 2 to the 256 power combinations are going to be valid inputs for ECDSA. So it's a little bit, the actual number is a little bit less than that. But for the sake of this calculation, we'll just consider, okay, yeah, the odds of generating a unique private key is 1 over 2 to the 256th power. So the chance of the same private key being generated is 1 over 2 to the 256th power times 1 over 2 to the 256th power, which is really, really astronomically low. So it is because of this probability of collision, because it's so low, like this is why we can consider randomly generating private keys to be secure. Okay. So the next step after we generated a private key, we want to be able to generate a corresponding public key from that from the unsigned integer. So we do this by running through ECDSA. Right. So again, Bitcoin uses ECDSA to produce public keys, and part of the algorithm involves doing some calculations through an elliptic curve. And the particular elliptic curve that Bitcoin uses to generate their public keys is called SECP256K1. And you can see on the right-hand side of the screen a visual representation of that elliptic curve. You also can see the mathematical formula that denotes this curve. Okay, so using a private key as an input, that 256 unsigned integer, we can generate a public key by performing point multiplication, or also known as elliptic curve scalar multiplication. And what point multiplication basically is that it's essentially like repeatedly adding a point onto itself. But we're not going to go into like more like the granular math behind that, because we consider it out of scope for this lecture. But the key takeaway from this slide is that point multiplication or scalar multiplication is a trapdoor function. Or in other words, it's similar to a cryptographic hash function. It is a one-way function, meaning that it is, because it's a one-way function, if you just have your public key, it is like very, very difficult to reverse engineer the private key from that public key. And we'll find that if we decide, okay, let's try recovering the corresponding private key from a public key. So we have a public key, and yeah, for whatever reason, we want to try recovering the private key from it. So we'll find that the time it takes to recover the private key would take around 650 million billion years. So yeah, takes a dummy long time, so it's not really worth doing it. And because it takes such an astronomically long time to recover a private key from a public key, is considered secure, because for 99.9% of people, they're not going to go through the pain of doing this. All right, so the next step, so now we've generated a public key from a private key. Now we want to create a public key hash from the public key. So in Bitcoin, in order to create this public key hash, they'll run the public key through two different cryptographic hash functions. One of them being SHA-256. I'm sure this cryptographic hash function looks familiar to a lot of y'all at this point. And the other cryptographic hash function they use is CRYPTOGRAPHIC. So using these two cryptographic hash functions, they'll create a unique public key hash. And then with that unique public key hash, we'll create a BEC32. We'll create a BEC32 Bitcoin address. So some fun things to note about BEC32 is that it's a relatively new address format for Bitcoin users. It is definitely not the original address format, and BEC32 was implemented as a part of implementing SegWit as an upgrade to Bitcoin protocols. And why did they change the address format? BEC32 was considered more efficient for blocks compared to previous address formats. So exciting times we live in. Times of change. All right. Yep, that's it for like how private keys, public keys, and addresses are generated. Any questions? I'm going to look in the chat. Okay. Again, if you have any questions later down the line, then feel free to just ask them in the Q&A. The private key slide? Of course. Yep. Quickly run through it? Okay, yeah, I can try. Okay, so, all right, so private keys on Bitcoin are at the end, at the very core, just 256-bit unsigned integers, and they cannot be generated using traditional regular random number generators because traditional random number generators are not actually truly random because they are all deterministic to some degree. So we want to generate private keys using a cryptographically secure random number generator. And of course, there is the question of, and the chances of two people generating the same private key is extremely low, just because of how the math works out. I hope that was sufficient. Okay, awesome. Okay. All right, so let's move on to the last section for this lecture, where we'll be taking a brief look into Bitcoin script. All right, so let me get my notes up again. Okay. All right, so remember the UTXO model. If you recall from previous lectures, I believe this was covered in lecture 1. So if you recall from previous lectures, Bitcoin uses a UTXO model to facilitate transactions. So these transactions simply map inputs to outputs. And in this model, spending Bitcoins is equivalent to redeeming previous transaction outputs. So new piece of information we want to introduce in this slide is that these transactions also include the signatures of the owners of the funds, whether that be like the original sender or the recipient. Okay, so we're going to take a brief look into the actual code that represents a transaction on the Bitcoin network. So this is actually very close to the actual representation of a Bitcoin transaction. It's just formatted to be readable by humans rather than machines. So it's not in ones and zeros and ones. All right, so so we can see that transaction can be primarily broken down into 3 parts. You have the metadata, the inputs, and the outputs. And you'll see that especially in the inputs and outputs section, you'll be able to identify and recognize, the UTXO model is coming through. All right, so first let's take a look at the metadata portion of the transaction. So the metadata is comprised of 6 variables, and really 3 of them are of primary interest to us. And one of them is the hash variable. And the value of this hash variable is simply the hash or ID of this particular transaction. The other 2 variables of interest are VN and VOUT. VN indicates the number of inputs this transaction is taking in, and VOUT is the number of outputs this transaction produces. So VN is essentially is a number of UTXOs that you are breaking / redeeming, and VOUT is the number of new UTXOs that you are producing with this transaction. There are also a couple other variables like version, lock time, and size of transaction, but for the purposes of our lecture, they're going to be considered less important. All right, so now that we've covered the metadata, let's take a look at the input portion of the transaction. So if you remember from the metadata section, VN was 2, so that indicated this transaction had 2 inputs. And now we see in the input section, there are 2 sections for 2 inputs. So, and these sections both include a hash that stores the ID of the previous transactions that are being redeemed. Also include the index of the input from in the previous transaction. And they also include a signature that the signature used to redeem the previous transaction outputs. All right, and the final section we'll take a look at is the output section. And the output section contains two pieces of information that are very interesting. So the value indicates how much the output amount, like how much Bitcoin is being sent overall in this transaction. And it also outputs a script. Okay, so from the transactions, we can see that output addresses are actually scripts. So in this particular example, the output script can be interpreted as this amount can be redeemed by the public key that hashes to this particular address, which is the really long gibberish up here. And we also require a signature from the owner of that of the recipient's public key. Now, so the question is, like, why wasn't Bitcoin designed to just basically like explicitly like assign transactions to particular public keys? Well, they chose not to do that because it was considered a little bit limiting. If you make all your inputs and outputs scripts, it's a little bit more flexible for future extensibility of Bitcoin. All right, so the last thing we're going to go over is we're going to discuss just very briefly about the language that was built specifically for Bitcoin. And you guys may know this language as Bitcoin script. So two really important points about Bitcoin script is that it is a stack-based language, and it is a relatively rudimentary language compared to other common programming language that are used today. It's simple. It is deliberately designed to be not Turing complete. And because it is not Turing complete, it can't support functionalities such as loops. And it was deliberately designed to be this way because honestly, for Bitcoin's needs, you don't need anything more complex than that. But this is a key point to keep in mind, especially in preparation for future lectures, especially lectures about Ethereum, because you'll find that this is a key difference between Bitcoin and Ethereum, and because their languages are designed differently, they can provide different services. But yeah, that is the end of the really quick Bitcoin script section. And it is the official end of the lecture. But may I ask if you guys have any questions? I'll take a look at the chat. All right, that's basically the end of the lecture. Yay, thank you everyone for coming by. I'll definitely stick around for a little bit to answer any remaining questions about like ECDSA and like signature generation and verification and stuff. So, but yeah, thank you all for coming. It was awesome to see so many of y'all. Thank y'all for coming.